Here is an explanation for the answer to final exam question number 48 in Alternative Energy Demystified, 2nd edition. If you have the printed book, please see page 320. We can obtain perfect diamagnetism if we can get a sample of material to do what? Well, what is perfect diamagnetism? We need to know, first of all, what that means. Perfect diamagnetism means that an object that has this property of perfect diamagnetism expels all of the magnetic flux that comes near it. So in contrast to something like a piece of iron, which concentrates magnetic lines of flux, or even a piece of glass or plastic which has no effect on magnetic lines of flux, a material that exhibits perfect diamagnetism actually expels magnetic lines of flux. So it's pretty hard to get an object or a sample of material to do that. We don't find them very often in nature, and if we do find any kind of a diamagnetic material that dilates magnetic lines of flux, it doesn't do it very much. So what do we want to do this for anyway? Why would we want to do this? Well, we'd want to do it in order to get magnetic levitation, which I'll show you an example of in just a second. Concentrate magnetic lines of flux? Well, no, we certainly don't want to do that, and it's impossible to concentrate magnetic flux to an infinite extent anyway. That would be perfect ferromagnetism, not perfect diamagnetism. How about choice C, accommodate an alternating magnetic field? Well, any kind of a material will do that, except a perfectly diamagnetic material. That will expel magnetic lines of flux, so it'll also expel an alternating magnetic field. So C is definitely wrong. Now we've ruled out choices A and C. D, behave as a powerful enough electromagnet? Well, no, that would be a ferromagnetic substance or material. E, do all of the above? No. Obviously then, we can pretty much eliminate it down to choice B. Act as a superconductor. Well, definitely so. That is definitely what a superconductor can do, and it is one of the most outstanding characteristics of superconductors. So, suppose that we get a superconductive material, a superconductive disk. How do we do that? Generally, we have to chill it down very close to near absolute zero, which is minus 273 and a fraction degrees Celsius, or minus 459 and a fraction degrees Fahrenheit. Pretty cold. Colder than we normally see on Earth. Well, we never see anything close to absolute zero on Earth. So we have to do things like liquefy helium, and it's very difficult to do that, but it can be done. It has been done, and when that happens, certain metals become superconducting, meaning that they lose all of their resistance. When that happens, they tend to become perfectly diamagnetic, and you get this repulsive force whenever you have a magnetic field near it. So, for example, you could have a bowl like this. This is supposed to be a cross-section of a bowl with a bunch of electromagnets in it. These are AC electromagnets, but they could, in this case, also be DC electromagnets. We would get repulsion, and thereby we would get magnetic levitation. And that is one of the reasons why we are so intent on getting superconductive materials, so that we can have this perfect diamagnetism, and that's one way to get magnetic levitation. But getting back to the question itself, we can obtain perfect diamagnetism if we can get a sample to become a superconductor. A superconductor, lose all of its electrical resistance.